So remember that every linear transformation can be isomorphically mapped to a matrix. So we would like to know, is there a matrix version of the condition for a matrix having an inverse? Okay, and it turns out there is. And that condition is simply that the matrix, and I already wrote this, but now we're going to go back and sort of prove it, has an inverse if the determinant of the matrix does not equal 0. Okay? So what we want to do now is we want to sort of develop some of the machinery that goes into showing this. And this machinery will sort of be a generalization of what you've already known, and that is how to take a determinant. Okay? So if I gave you a matrix A, B, C, D, E, F, G, H, I, and I said find the determinant, what would you do? So what do you do? Somebody tell me. Okay, I'll draw a name. Matthew. Matthew, what do you do?
So I would start with either a row or a column, and you know, there's like a sign pattern that you have to follow when calculating the determinant. So, for instance, A times like EI minus HF, and then D times well, negative D times BI minus HC, and then the last one.
Yeah. So how many of you are familiar with the fact that you can use any row or column to calculate the determinant? Okay, I mean, many people when they first learn to calculate a determinant, they just use the top row. But it turns out that that's a very democratic procedure, and you can actually use any row or column to do it. Okay, so all we want to do is notationally we want to lay out that process. Okay, but intuitively it should make sense. So so here we go. Here's the process. First and foremost, we have that the determinant of A is the sum over little j of one of the rows being frozen, okay, times what's called the cofactor of A, that same row, little j. This is picking a row and freezing it, but we can also pick a column and freeze it. In that case, our expression goes as follows. A sum over little j, capital J, cofactor A little j of j. Okay? So you can fix a row and you can do everything, or you can pick a column and do everything. Okay? And this capital J can be 1, 2, 3, 4 up to n. All right? Now, to define the cofactors, we have that a cofactor is minus 1, and I'm not going to write equals because this is a bunch of words, but it's minus 1 I plus j. So this is the cofactor of the ijth element. Okay? So we do minus 1 I plus j, where these are the row and column labels, times the determinant of the matrix left by ignoring the ith row I row and j column. Okay? All right, now we're not going to prove that. But there is another example, which is going to become very valuable, where we say, well, I don't necessarily have to take j here to be the same as the j there. I could consider what this expression would look like if I picked a different row here and a different row here. And in that case, all that we have to do is slap a delta function on the left side. So we could say delta kj det A is sum over j similar version of it for picking a row. I mean a column. Okay, I won't write that down. All right? Now, this might not be obvious, so let's actually look at a really concrete example of how this works out. So consider the matrix, and we'll just do a 2 by 2 for simplicity. All right, if I choose capital K equal to capital J, then this reduces to this definition, okay? Because obviously the delta function is just a 1 if the indices are the same, okay? So what we would like to do is explore if K is different than J in this example, okay? So if K is different than J, what is the delta function? It's 0, okay? So the left-hand side is 0. So we have 0 equals, and now we can say, all right, well, I mean, this has only got 2 values, 1 and 2, so we can pick K to be 1 and J to be 2 for simplicity. So we could say sum over J, A1J cofactor A2J. Okay? All right. So, well, let's do this. So, A1, so we're going to sum over J, so J can start out at 1, so we're going to have A11 cofactor A21 plus A12 cofactor A22, okay? Element A11 is obviously A, and then the cofactor is minus 1 to the 2 plus 1 times what's left if you block out the row and the column that A occupies. So that is D. Yeah. No, sorry. Hold on a second. Oh, no, sorry. This is A11, this is A21. So this is the second row in the first column. So what's left is B. So this is A21, I was thinking 1, 1. So for 2, 1, we're blocking out the second row in the first column, so what we're left with is B. Okay? And then for A12, first row, second column, this is B, and then the cofactor is minus 1, 2 plus 2, because they're taking the cofactor of the A22 element. And then the A22 element, well, the A22 element is D, so we're blocking out C and B, and we're left with A. What's that equal to? 0. Okay. Because this is going to give me a minus, this is going to give me a plus, and then it's AB minus BA. Okay? So everybody see how this works? All right, good. This leads to a definition, which will be very valuable in just a moment. And that is the definition of the classical adjoint. Of an n by n matrix is ADJA. So this is going to have elements. So this is a matrix. It's going to have elements labeled by I and J, where these are equal to the cofactors of the elements labeled with JI. Okay? So make sure you pay attention to the fact that the indices here are switched from the indices there. Okay? Now, if we take this, and this is a definition. Okay. If we take this and we shove it into this theorem, we're going to get an interesting result. So we can say delta kj det A is, and I'll just very quickly write up. Okay? So cofactor AJI is the adjoint of AIJ. So I can write this as sum over J, AKJ times the classical adjoint of A, where we're talking about the term of that, which is A little j, capital J. Okay? Again, notice the switching of the indices. Now, this is an element of a matrix. This is an element of a matrix, but now we're summing over the adjacent indices. Okay? So that means that we can also write this as A adjoint of A, where we're looking at the capital K, capital J element of that. All right? If we go the alternative route and we use this version of this expression, which I didn't write, then we'll end up with something very similar. We'll just end up with adjoint of A times A, where we're looking at the capital K, capital J component. Okay? Now, this is a term-by-term equivalence for this guy and this guy, or this guy and this guy. But here's the nice thing. If your term-by-term equivalence actually uses the same ordering of the indices, then you can literally say this matrix is equal to this matrix. Does that make sense? Notice I can't say this matrix is equal to this matrix because the subscripts are interchanged. But if the subscripts in each expression have the same order, then this is a term of the matrix is equal to a term of the matrix. But since they're all labeled the same, you can just say this matrix is equal to this matrix, right? Now here's the big question. What matrix corresponds to that? The identity. Does that make sense? Okay. So I can write I times det A is equal to A adjoint of A, which is also equal to the adjoint of A times A. Okay? Everybody follow that? Okay, good. This leads us to a powerful result. There you go. Let's prove it. Suppose det A does not equal 0. If det A does not equal 0, then we can take this expression and we can say, oh, the identity is A, so we'll do it this way. It's the matrix A times the adjoint of A divided by the determinant of A. Or we can use this form, and we can say it's the adjoint of A divided by the determinant of A times the matrix of A. Okay? So if the determinant is not 0, then we can divide by the determinant. That's a rule you all are familiar with. Okay? But what is this telling me? What is this result telling me? What is this right here?
It's the inverse.
It's the inverse of A. So if the determinant of A is not 0, then you can find the inverse. The inverse exists. Okay? If you want to prove the only if part, well, we did this last time, but I'll just repeat it. If there exists an A inverse, then we can say A inverse equals the identity. That's the definition of an inverse. And then by taking the determinant of this and breaking it up into a product of determinants, which we know we can do, this is equal to the determinant of the identity, which is of course 1. Okay? Well, if the product of the determinant of A and A inverse is equal to 1, then A can't be 0. Okay? We proved this last time. It's this component of it which we needed this machinery to prove. And there you go. Okay? So, as promised, this is the matrix version of does this thing have an inverse? All you got to do is calculate the determinant. If the determinant is not 0, it has an inverse. So too does any linear transformation that this matrix is isomorphic to. Okay? Make sense? All right, good. Okay, so let's consider, let's consider, well, I don't know, let me see, 1, 2, 3, 4. Yeah, let me go through a really quick example of this just to show you how to do the calculation. Probably regret erasing this, but that's fine. Okay, so consider a rotation, which is a linear transformation, in R2. So we know this can be matricized by cosine theta minus sine theta, cosine theta. All right? And clearly, the determinant of R theta does not equal 0. It's cosine squared plus sine squared, which is 1. Okay? So there should be an inverse. Let's calculate it using this machinery. So R inverse is the adjoint of R theta over det R theta. Okay? I just erased it, but at any rate. So first of all, the 1 over the determinant factor, which is what we're calling the adjoint, is just 1 over 1 because the determinant of this is 1. All right. And then to calculate the adjoint, just as an example, all right, we're going to have the cofactors. And remember, we transpose this, okay? Because this thing right here, this set is the cofactor of the elements of R theta. It's the matrix of cofactors, but we want the transpose of it in order to get the classical adjoint. All right? So, yeah, you can just figure this out, and what you get is cosine theta, sine theta, minus sine theta, cosine theta, which you all hopefully recognize as the inverse to the transformation we started with. All right? Everybody recognize that? Okay. Now, This is an obvious example, which obviously has an inverse because it's just a rotation. Rotations always have inverses. Let's consider an example that doesn't have an inverse. And we shall float back to our favorite example of a linear transformation, and it's matrix realization. So let's consider D on Pn. Does that have an inverse? You should know this by now. The derivative acting on polynomials up to degree n. Does that have an inverse? No. Okay. The map is not one-to-one. Okay. If I take two different constants, if these are my vectors, okay, these both get mapped to the same thing when I take the derivative. So it's not a one-to-one map. Let's look at the matrix reflection of this, though. So if I want to do this in P1, just for the simplicity, then the derivative matrix takes the form 0, 1, 0, 0. And this is in the basis of 1 and t. And alternatively, in the basis 1 plus t, 1 minus t, it takes the following form. And this is not something that's obvious, it's something we did before, so I'm just reminding you. Okay? Now, in matrix form, there's a variety of ways we can figure out whether it has an inverse. First of all, an important observation is if this doesn't have an inverse, neither does this. Why? Duncan.
If it's like it doesn't matter which coordinates this basis.
Exactly, right. The only difference between these two is that you're changing the coordinate system you're using to describe them, but that shouldn't impact whether or not the transformation has an inverse. Okay? That's an inert ingredient to the transformation, independent of how you're describing it. Okay? So, looking at that list of 8 properties that I talked about last time, I'm not going to write them on the board again. Can anyone tell me what property you could apply to show that this doesn't have an inverse?
Is it a column that's all zeros?
Yeah, it's got a column and a row, which is all zeros. If any matrix has that, it doesn't have an inverse. Okay? What about this one? Oh, by the way, this doesn't have an inverse, therefore this doesn't. But can anyone identify what property we might use here?
There's 2 rows that are put on.
Yeah, if you have 2 rows or 2 columns that are equivalent, then it's going to not have an inverse. Anything else?
Should we say the determinant is 0?
Pause. No, we're going to check that at the end. Any other rule? So I'm asking you this because if I give you a 200 by 200 matrix and I ask you, is it invertible? You might not want to calculate the determinant if you can use one of these tricks.
The columns are linearly dependent.
Exactly. In this case, this column is a linear combination of this one. It's just it multiplied by -1. Okay? But last but not least, you could just take the determinant in this case. Okay? The determinant's obviously 0. All right? Okay. So finally, and this is just finishing up what we tried to get to last time, if you have a change of basis, and I'm just going to formally say this, but we've already hit it, if A is related to A prime simply by a coordinate change, then, and we'll just go ahead and write it down, det A is automatically equal to det A prime. So the determinant doesn't change. This is a theorem that can be proved. We won't go through proving it. But obviously this implies that if A has an inverse, then A prime has an inverse and vice versa. Okay? Where again, the A to A prime is just a coordinate change in the description of the linear transformation. Okay, there we go. Now we're going to change gears a bit and talk about something else, but we're going to use these results. And this will be a topic which is fairly familiar to you. All right. So generally, a linear transformation, or the isomorphic matrix for that transformation, takes a vector in a vector space and gives you back a different vector, right? Always? No. Okay. What if a linear transformation takes a vector and gives you back, takes a vector, not a general vector, but a particular vector, and gives you back that same vector, maybe with a rescaling? Anybody familiar with that? What do we call it? It's an eigenvector. Okay. So let's explore eigenvectors and their associated eigenvalues. All right. So again, we're not looking at the action of the linear transformation over all the vectors in the space. We're really interested in finding elements of the vector space such that the linear transformation acting on them gives back that vector with some multiplicative factor. Okay? So the expression, of course, which you're all very familiar with, is that the linear operator acting on an eigenvector xi is the eigenvalue associated with xi times the linear times the eigenvector xi. This is not necessarily a basis vector. This is the same notation we use for basis vectors, but now we're having a discussion about eigenvectors. Okay, so these are not necessarily basis vectors. All right. So this is a linear transformation acting on a vector, but remember all vectors are isomorphic to n-tuples and all linear transformations are isomorphic to matrices. So we can attack this in matrix language, which we'll do, and that's probably what the language you've been approaching eigenvectors with previously. But let's first and foremost show the utility of it. So first of all, let's sort of inspire it. Remember last time where we had a linear transformation acting on a vector x, giving you a vector y, where you're given a and y and asked to find x. Okay, this is obviously where A inverse becomes useful. Because if you can find A inverse, then x is A inverse y. Okay? For these types of problems, if you have a problem that you're trying to solve that ends up of this eigenvector form, where you know, where you want to find both the eigenvectors and their eigenvalues, then this approach won't work. Okay? Fortunately, there is an approach that will work. Let's redo that. So let's take this equation and reorganize it a bit. So AXI minus lambda I xi equals 0. Okay? I think we can make that A minus lambda I xi, right? This is distributive, right? Caleb,
Yeah, we can.
I can do that
Yes.
every single time? Is this true?
Mm-hmm.
Yes. Is this true? All I've done is I've factored out the xi, man. You could do that, right?
Yeah.
Can you do it?
I'm guessing no, based on the way you're acting.
What is this?
Matrix.
What is this?
Scalar.
Yeah, yeah. What do we need? This is a matrix, this is a scalar. I want to make this.
Yeah. Do we use the identity?
Yeah, we just throw the identity in there. It's not necessary here, because this is a vector, and this is a vector, but here we need the identity. Okay? Make sense? I mean, this is a linear transformation of a vector. That gives you back a vector. So this is a vector, and this is a vector. Okay, at any rate. All right. So we can define, so we can call this mxi. And to have an interesting solution, well, actually, let's suppose if M inverse existed, so if M was invertible, what does that tell us? Chloe,
And
if M inverse exists, what is xi?
0?
It's 0. It's not very interesting. If 0 is your eigenvector, that's not that interesting. Okay? So we actually want M to not be invertible. Well, M is a matrix, and we want it not to be invertible. What do you think we're going to look for?
Determinant equal to 0.
The determinant of M equals 0. Okay? So we want determinant of M equals 0 for interesting solutions to this. Because if the determinant of M is not equal to 0, then the only solutions are xi equals 0. So I said we're going to use what we just proved. Well, here we go. Okay? All right. Now, if I expand what det M is, let me just say, det of A minus I lambda I equals 0. The only unknowns in this are the lambda i's, the eigenvalues. So we've reduced the problem here to at least a step where all we have is our unknowns or the eigenvalues. Okay? Now, the determinant of a matrix gives me a number, right? So how many lambda i's can I expect? So my better answer I'm going to call. Chad.
1.
1. You expect one solution for a lambda? I mean, this is a scalar equation. There's a lambda in it. There should only be one solution, right? Kind of.
Is it dimension of the matrix?
Why?
Because that's what I've always seen.
Okay, but why? Go for it.
So you need the matrix to be linearly dependent. So you're essentially for each independent component of the matrix, you have to make it dependent.
That
If it's
might,
rank 3, you're going to have 3 solutions.
you might have 3 solutions,
You might have 3 solutions.
but why?
Because you equations.
Get a polynomial of up to order n, so you can have n solutions.
Remember, the determinant of an n by n matrix gives you a polynomial of degree n. So this is a polynomial of degree n. It has n potential solutions. Some of them could be degenerate. Okay? But no more than n. That's important. You can have up to n solutions for the eigenvalues. Okay? All right. If A is a real matrix, then the eigenvalues should be real, correct? Who says they should be real? Who says no need for them to be real? There's a no need factor. I mean, remember, that's an equation that only involves real things. except the only solution is imaginary. Okay? So you might be looking at a matrix representation of a linear transformation where all the elements are real, and you might be like, oh, I need to find real. Nope. There can be imaginary solutions or complex solutions. Okay? So you have to open your mind. All right. So this is going to be a polynomial. We have to solve it for the lambda i's. But once we've found the lambda i's, we plug them back into here, and now this is an equation with one unknown. That's the xi's. Okay? And then we found our eigenvectors and our eigenvalues. Okay, this is a procedure you should all be familiar with. So let's quickly go through an example. Let's consider the vector space, which is basically R3. So we're talking about a 3-tuple over the field of reals. And let's consider the linear transformation whose matrix form is the following. So we're going to think in R3 about a rotation in the xy plane. Okay, so you all know what this matrix looks like. Cosine theta minus sine theta, cosine theta, and then 1 for what we're doing. OMZ. Okay? Where the theta here is not 0 or pi. So we want an interesting value of theta. Now, can we identify one eigenvector of this instantly?
One. Or the last column.
Yeah, so the last column, right. So we can say, let me see my notation here. Yeah, so we can say that an eigenvector is 0, 0, A, where A is arbitrary. Okay. Now if you just look at it, if you act on this vector with this matrix, all you're going to do is get 1 times this thing. Okay. So so we have Rxy times x equals x. So the eigenvalue in this case is just +1. All right. Now we want to find. So now we've just kind of used this eigenvector eigenvalue equation, but we want to use the tools that we've developed. So let's consider this from a different perspective. So clearly, first and foremost, the determinant of Rxy does not equal 0. Okay? Does that mean this won't work? No, because the determinant of Rxy not being 0 does not mean that the determinant of this is not 0. This could have a 0 determinant. Okay? So let's calculate it. So, okay, so we're going to have the determinant of Rxy minus I times lambda I equals 0. And let's actually use this solution to begin with. So we're going to start with lambda I equals 1. And I'm finding this solution, but I'm using the machinery. And now this is just going to become the determinant of cosine theta minus 1 minus sine theta, cosine theta, minus 1, 0, 0, 0, 0, 0. That's obviously 0. Okay? So now what we're going to do is we're going to treat the lambda i's as unknowns. So we're going to have the determinant. Actually, I'll just write it up here. I'll just sneak it in here. Save myself from writing. Okay? And this is going to give me cosine theta minus lambda I, cosine theta minus lambda I, 1 minus lambda I. theta, 1 minus lambda I. Okay? And if I multiply this bad boy out, this is going to give me lambda I cubed minus 2 cosine theta plus 1 lambda I squared plus 2 cosine theta plus 1, oops, whoa, lambda I minus 1. So there we go, we've got a cubic polynomial. And you can ask, what are the roots of this? Well, certainly, we have a lambda I equals 1 as a solution, but it turns out we have 2 more, and those are basically e to the plus or minus I theta. Okay? So we have 3 distinct eigenvalues for this transformation. One of them is real, as we expect, but 2 of them are imaginary. So let's look at what the corresponding eigenvectors are. First and foremost, if we're going to look at the first one, then this is going to be Rxy, x1 equals cosine theta minus sine theta, cosine theta, 0, 0, 1, 0, 0, times an unknown vector ABC, okay, is going to be, well, if I do my matrix multiplication and I do it correctly, this should be A cosine theta minus B sine theta, A sine theta plus B cosine theta, and C. And this should be equal to the eigenvalue times the original vector. So this should be equal to ABC. All right? Oh. This tells me that A is equal to B is equal to 0. And C can be anything. Which is exactly what we said this eigenvector was. Okay? So let's try one of the complex eigenvalues, and I'll just do the positive one. In this case, we have Rxy x2 becomes A cosine theta minus B sine theta, A sine theta plus B cosine theta, C equals, so we still have the same matrix acting on an unknown vector, so the only thing that's changing is the right-hand side, and in this case it's going to be e to the I theta A, e to the I theta B, e to the I theta C. And it turns out this has a solution where if minus B is equal to AI and C is 0, remember theta is not 0 or pi, then this is an eigenvector. Okay? So at the end of the day, we get 3 eigenvectors corresponding to these 3 eigenvalues. Where did I write down my eigenvalues? Over here, yeah. So we can write down the 3 eigenvectors associated with them. And these are going to be 0, 0, C, x2, which I should write it like this. x2 is A minus IA 0, and x3 is minus IB B 0. Okay? Where A, B, and C can be anything. 0, nothing. Okay? So the story we just learned is that a 3 by 3 matrix has 3 eigenvalues, which are all distinct, and it has 3 eigenvectors. Therefore, we can say that an n by n matrix has n distinct eigenvalues and n distinct eigenvectors, right? Hell no. got lucky with this one. This is a 3 by 3 matrix. It happened to have 3 distinct eigenvalues, and each of them had a distinct eigenvector, but that is not something we're guaranteed. Okay? Let me give you an example of where that doesn't happen, and then we'll introduce some notation. Actually, I'll introduce the notation and then I'll give you the example. The algebraic multiplicity of an eigenvalue is the number of times it appears as a root to det A minus I lambda equals 0. Okay? We're going to call that the algebraic multiplicity. And I'll show you an example where the algebraic multiplicity is not 1. There is separately the geometric multiplicity. Of an eigenvalue. Seth. Oh, Seth.
Yes?
Any guess on what the geometric multiplicity means? So remember, you have a polynomial, and it might be that, lambda I equals 1 is 2 solutions to it. So that would have a geometric multiplicity of 2. It might only be 1 solution, in which case geometric multiplicity is only 1. Or sorry, the algebraic multiplicity. What is the geometric multiplicity? What do you think that is? Of an eigenvalue. So let me give you an eigenvalue, and I'm going to ask you, what is its geometric multiplicity? What do you think that means? Any guess?
I don't know.
What is associated with an eigenvalue?
It's eigenvector?
Eigenvectors.
Yeah. Oh, so how many eigenvectors it applies to?
Exactly. How many eigenvectors are associated with the eigenvalue corresponds to its geometric multiplicity. These are very different notions, okay? And these have to be linearly independent. Okay? So let me give you some examples. Well, let's start with a quick theorem. The geometric multiplicity is less than or equal to the algebraic multiplicity. Okay? So if an eigenvalue only appears as a solution to the polynomial that comes from the det A minus I lambda equals 0, if it only appears once, then the most number of eigenvectors you can associate with it is 1. If it appears twice, you can have up to 2, but you might just have 1, or you might have none. Okay? All right, so let me give you an example. A is going to be 1, 0, minus 1, 1. And we can very quickly figure this out if I do the determinant of 1 minus lambda, 0 minus 1, 1 minus lambda. This is just 1 minus lambda squared. Daniel, what's lambda? 1. But it's a quadratic, so there should be 2 solutions. Another one, exactly. So we have two eigenvalues and their value is degenerate. What is the algebraic multiplicity of the eigenvalue 1? It's 2. So does that make sense? This is quadratic, so it has to have two solutions. Those two solutions happen to be identical, so the algebraic multiplicity of the associated eigenvalue is 2, okay? Well, let's now check out the eigenvectors. A acting on AB, well, the eigenvalues are 1, so I'll just say this is AB. If I hit the unknown AB with this matrix, then I'm going to have A minus A plus B is equal to AB. How many linearly independent solutions do this exist? What is the solution? So A and B are unknowns. What are A and B? A has to equal what?
B,
If A is equal to B, then this is 0,
or A,
and that's,
one has to be.
it has to be 1/2 of B?
No, A has to be 0.
A has to be 0, exactly. So the solution of this is 0B. That's it, that's the only solution. I mean, I could do, 0K, but that's a linearly dependent, okay? So what is the geometric multiplicity of this eigenvalue? 1, okay? So the algebraic multiplicity of an eigenvalue does not have to agree with the geometric multiplicity. Here's an example, okay? It can never exceed it. So you couldn't have 3 eigenvectors associated with this eigenvalue because it's only got multiplicity, algebraic multiplicity of 2. Now, for a linear transformation, let me see. Yeah, I'll just erase it. For a linear transformation, it always has at least one eigenvalue and one eigenvector. At least one. Okay? But there's no guarantee, obviously, that you're going to have enough eigenvectors to span the space. Of course, the largest number of linearly independent eigenvectors it can have is n, where n is the dimension of the matrix representation or of the vector space, either one. Okay? And now let's make another observation. If two matrices are similar, that is, they are related by a similarity transformation, i.e. A is similar to B, if A can be obtained from B via a similarity transformation. Oh man, why am I wearing my damn mask? I put you guys 6 feet away and I forgot to take my mask off, at any rate. Then they have A and B have eigenvalues. Actually, sorry. They have the same eigenvalues with the same geometric multiplicity. Okay? So, if I do a similarity transform on a linear transformation, this is acting on it with some other transformation whose inverse exists. That's the inverse on the left and the original transformation on the right. Then A is similar to B. Well, if A is similar to B, then they're going to have the exact same eigenvalues, and those eigenvalues are going to have the same geometric multiplicity. But notice, I did not say they're gonna have the same eigenvectors. Okay, they can have different eigenvectors, and they generally will, but they will have the same numerical values for their eigenvalues. Okay, see, part of the proof of this, we're not gonna do the whole proof, but consider the following eigenvalue, eigenvector equation. B acting on xi gives me lambda I xi. And what we're going to do is we're going to apply C negative to the left of this. And we're going to apply it to the left of this, but this is a scalar, so I can move it outside of the application of the operator C minus, or C inverse. Okay? And now what we're going to do is we're going to insert one of those identities. That's a trick that we always use in proving things mathematically. So we're going to use the identity C times C inverse. And inserting that, what we're going to get is C inverse B C inverse xi is equal to lambda I C inverse xi. Oh wait. This is just A. This is the linear transformation A. Okay. But don't let that C inverse fool you. That's just a different vector. So we might call it yi. Okay. So as I argued, if two matrices are similar, they're going to share eigenvalues. But they're going to have different eigenvectors. Okay? And they share the same geometric multiplicity. So if you've got k eigenvectors associated with linear transformation B, then you also have k eigenvectors associated with its similar transformation A. All right? We're doing pretty good today. Now let's take this and apply it to diagonalization, which you're all probably pretty familiar with. Let's see. Yeah, let's trace this. Okay. So this entire story simplifies quite dramatically if we're dealing with a diagonal matrix, obviously, right? Okay. So a diagonal matrix is just one where we have entries on the diagonal and zeros everywhere else. Clearly, this one's easy to solve. Det d minus lambda I is, well, it's the product over all of the indices. But this just tells me that my lambda i's are equal to the dii, the diagonal elements. Okay? So, and these are all non-zero, by the way. So the diagonal elements of a diagonal matrix are the eigenvalues of the matrix. All right? Now, if we combine this with the eigenvalues common to both a diagonal matrix D and any matrix which is associated to D by a similarity transformation, then what we find is the following. D is P inverse AP, where P is the matrix composed of the eigenvalues, or sorry, of the eigenvectors of A. Okay? notice for a diagonal matrix, you're going to have n eigenvalues, and each of them is going to have an associated eigenvector. So you're going to have n linearly independent eigenvectors. Well, so will A. Okay? Obviously, the determinant of the diagonal matrix is not 0. Okay? So this P inverse must exist. So what we can do is, we can say if we start with A, so starting with a diagonal matrix is a really simple story. What we want to do is we want to start with a more general linear transformation A. Then the only way that P exists is if A has a set of eigenvectors which span the space. Okay? So let's go back to our example really quickly. So remember, if A is Rxy, it's a rotation of the xy plane in 3 dimensions, then we have the solution lambda 1 equals 1, x1 equals 0, 0, c. Lambda 2 is e to the I theta, x2 is a minus I a 0, and lambda 3 is e to the minus I theta, x3. And x3 is minus b, b 0. Wait a minute. Isn't this linearly dependent on that? Can't I just multiply this by an I and get that? No.
No?
Multiply this by an I, what do you get? What do you get?
You get B and IB, so it's not negative.
Yeah, it's funny, if you multiply this by an I, this will become B, and this will become IB, which is not linearly dependent on that. I see that? Okay, it's the weirdness of imaginary numbers. Okay, so we know that P is the matrix formed by the eigenvectors. So P is 0, 0, C, A, minus IA 0, minus IB, B 0. And then using this, we can find the inverse. Multiply Rxy by it. And just so that you have an example of an inverse. And then we want to multiply that by the transformation matrix. And lastly, by the matrix itself. What are you going to get? Who can do that matrix multiplication in their head really quickly? Look, folks, I just took a matrix, A, and I just did a similarity transform using P as the matrix formed from the eigenvectors. What should this give me? It should give me the diagonal matrix with the eigenvalues, which it will if you do your matrix multiplication. Okay? Now, let's look at a counterexample where it doesn't work out so nicely. So if instead I consider 1A01 as my linear transformation, then going through the solution process, this only has one solution. X1 is B0 with the associated eigenvalue 1. Does this span the space? No, it's one eigenvector in a two-dimensional space. Can you diagonalize this? Nope. Okay. All right. Finally, we have the following. If the determinant of A equals 0 and the eigenvectors span the space, which A acts on, then AX equals B, this is an equation, has a solution if and only if B is a linear combination of eigenvectors for which lambda I does not equal 0. Okay? Now instead of proving this, I'm just going to show you an example. Okay, so consider the following linear transformation, and we'll just keep it simple. So it's a diagonal matrix. Okay? So these are zero. These are zeros everywhere you need them. It's just the diagonal terms that we're worried about. All the other terms are zeros. I just get tired of writing in zeros everywhere. What's the determinant? It's 0. Okay. Interesting. All right, so let's find, this is the condition that we need here. So this could be an interesting story. Let's find the eigenvalues. A minus lambda I, well, it's already diagonal. So lambda 1 is 0, lambda 2 is 1, and lambda 3 is 2. We don't even need to solve this. It's a diagonal matrix. Okay, the diagonal elements of the eigenvalues. So now let's try and find an eigenvector, starting with the first eigenvalue, 0. This tells me that x1, which is A, 0, 0, everybody see that as a solution? If I hit this vector with this matrix, I'll get 0. Okay? And linearly dependent eigenvectors are basically the same eigenvectors, so we might as well set that A to 1 for simplicity. Now let's find the second one. So we're going to do 1. And this is going to have the solution x2 is 0, b 0, which we can just call 0, 1, 0. for the third, 2x3 using the eigenvalue 2. This is going to let us find the eigenvector corresponding to that, and that ends up being 0, 0, c, which we can of course call 0, 0, 1. Okay? Now, what we want to show is this. So let's do it. First of all, yeah, so we got ax equals b, and we're going to look at two cases. First, we're going to look at b is k x2 plus j x3. Okay? Where the b function in this case is a linear combination of eigenvectors for which the eigenvalue does not equal 0. Okay, the second and the third don't equal 0. All right? So let's see what ax equals b looks like in this case. Of course, we have 0, 1, 2 times, and the unknowns for the vector will be u v w equals 0 v 2w, which is going to be equal to 0 k j. That's just evaluating this b using these eigenvectors. Okay? Well, this has a solution. U can be anything. V has to be k, and 2w has got to be j. Make sense? Okay. So as promised, if the thing on the right-hand side of this equation is a linear combination of eigenvectors which don't correspond to eigenvalues of 0, okay, then there's a solution. Now let's look at the alternative. Let's consider b being hx1 plus kx2 plus jx3. Now it's a linear combination of all three eigenvectors, which includes the one with the eigenvalue of 0. And I just very quickly want to show you this doesn't have a solution. So again, if we set up our multiplication, is there a solution? I mean, h is non-zero. There's no solution. Okay? In fact, you can see that h is the problem, right? Okay, any questions? All right, sorry I ran a couple minutes late. We were a couple minutes late getting started. Your homework will be updated a little bit later on tonight, okay? And once again, the quiz will be next Thursday. Yes?
What did you decide to do about the homework we just have one extra class on?
Sorry, say it again?
What did you decide to do about the quiz next week with not having 4 homeworks on it?
No. The quiz next week will only have it will only cover the material we covered this week.
Yeah.
Does that make sense?
Yeah, I was asking what your plan is to do with the material we cover on Tuesday, I guess.
With the material we cover next Tuesday?
Yeah.
That and the material we cover that Thursday will go on the quiz the following week. Does that make sense?
You mentioned before that we were one day off of the quizzes, and so I think that's what he's asking about.
Well, let me think. No. We're not. We're actually not one day off with the quizzes because I gave you a quiz today over the first week's homework, and then the second week's homework you'll get a quiz next Thursday. Does that make sense? I'm confused. Am I got this wrong?
I think you originally planned.
Yeah, I had originally planned to give you a quiz over all of the homework leading up to that quiz day, but then I decided, no, I'm just gonna give you a quiz from the week, the previous week's material. So your quizzes are only gonna cover 2 homework sets over 2 lectures worth of material. That fixed it.
Okay.
Does that make sense? Okay, good. Throw this on. Okay.